presentation for my project work, which has the title of MPE Growth Characterization of Silicon Germanium Virtual Substrates. Here's the outline for my presentation. First, I'll give you the introduction about the virtual substrate, then I'll tell you about the objective and motivation for the present work. Then I'll tell you about the experimental techniques we used in this project work, and then the experimental procedures we followed. And then I'll present and discuss the results, and then I'll summarize the discussion, and then some suggestions for the future work. First, I'll define the virtual substrate. As we know that the germanium has 4% larger lattice constant than silicon. And the lattice parameter for bulk silicon germanium alloy depends upon the germanium content, and which we can calculate using Vegard's law. If we grow this silicon germanium layer on silicon, it will have a compressive strain. And when this strained silicon germanium layer exceeds the corresponding critical thickness for the given germanium concentration, the layer will get relaxed. So the whole structure having highly relaxed silicon germanium buffer layer of high quality plus the silicon substrate will be called as the virtual substrate, as you can see in this figure. So what should be the desired properties of these silicon germanium virtual substrates? They should have highly relaxed thin silicon germanium epilayer. They should have higher germanium content and very smooth surface. The commercially available virtual substrate, which are grown by CVD technique, and they have a graded germanium concentration in the silicon germanium layer. They have high relaxation, very smooth surface, but they have very thick silicon germanium layer. And have the purpose of having thick silicon germanium, the reason, for having this thick silicon germanium layer is the grading rate for germanium concentration in the silicon germanium layer. That is 10% per micrometer, which makes this whole structure very thick. Why do we need these virtual substrates? As we know, the lattice constant for this silicon germanium relaxed buffer layer that decides the strain engineering in epitaxially overgrown structures. And this strain engineering in epitaxially overgrown structure can change the optical and electrical properties of these overgrown structures. For example, if a silicon layer is grown on these virtual substrate, it will have a tensile strain in it. And this tensile strain can increase the charge carrier mobility in this strained silicon channel. And if we use this strained silicon channel in a transistor, that can switch at higher frequencies. So where we can use these virtual substrates? They have application in high-speed field effect transistors. They can be used as a growth template for the integration of 3-5 materials on silicon. They can be used for the fabricating of detectors in optical communication. So the objective of this diploma work is to study the growth of silicon germanium virtual substrate containing a thin silicon germanium epilayer to achieve silicon germanium top buffer layer with high germanium content, high relaxation degree, and low surface roughness. To grow these virtual substrate, we use two-step growth scheme. In the first step, silicon germanium layer was grown at very low temperature, and in the second step, the silicon germanium layer was grown at very high temperature. And the purpose of this very low temperature growth step is to introduce a lot of point defects. So these point defects can help to promote the relaxation during growth. They can reduce the threading dislocation density, and they can improve the surface smoothness of thin silicon germanium buffer layers. Idea of having this very low temperature growth step was adopted from the work by E. Casper. And then finally, we compare our grown virtual substrate with a commercially a virtual substrate to check their quality. During this project work, To grow these virtual substrate, we use molecular beam epitaxial technique, and for the characterization purpose, we used reflection high energy electron diffraction for the real-time monitoring of growth, high resolution XRD 2D reciprocal space mapping to study the crystal quality and to calculate the germanium content and the strain relaxation, and to study the surface morphology. Atomic force microscopy was used. Here in this slide, you can see the MBE growth setup. During this project work, we used Balzer UMS 630 solid source MBE system equipped with reflection high energy electron diffraction setup to monitor the growth conditions. Here in the figure A, you can see a typical reed setup. In reed, an electron beam hits the surface, and these, after hitting it, it's been diffracted, and this diffracted beam hits the fluorescent screen, and it produces the pattern called the reed pattern. There would be different kind of a reed pattern for different surface morphologies, as you can see in figure B. If the surface is very smooth, then there will be very bright spot in a circular order. If the surface is polycrystalline, then we'll see the rings called the amorphous rings. Then if the surface have 3D island growth, then we can see the spotty features, or also called the bulk pattern. Then if the surface has 2D island growth, then we can see the streaky pattern. In high resolution XRD 2D reciprocal space mapping, we used Phillips Expert diffractometer with copper K alpha radiation. A map was completed by taking several couple of omega 2 theta scans for a range of omega. Two types of reciprocal space maps were taken. A symmetric reciprocal space map was taken around 004 reciprocal lattice point, which provides the information about the crystal quality and the lattice blend tilt in between silicon germanium layer and silicon substrate in 110 in plane direction. And asymmetric reciprocal space map taken around 113 reciprocal lattice point that provides the information about the lattice mismatch in parallel and perpendicular direction to the surface. And using this information, we calculated the germanium content and the relaxation degree in the surface. As I have mentioned earlier, to grow these structures, we followed two-step growth scheme. The purpose of having very low temperature growth silicon germanium layer is to introduce a lot of point defects, and the thickness in this very low temperature growth step was kept above the equilibrium critical thickness, that was around 20 nanometers. And the purpose of having high temperature silicon germanium growth layer was to anneal out these point defects and to grow a thick layer of about 70 nanometers beyond the critical thickness to trigger the strain relaxation. The thickness values were decided on the basis of a theoretical model given by Matthew, Blacksley, and People and Bean, which you can see in this figure, which shows the calculated critical thickness for silicon germanium grown on silicon. And we followed this bar in this project work because we try to grow the silicon germanium with the 40% germanium concentration. And this black region represents the thickness for very low temperature growth mode, and this line part represents the thickness in high temperature growth mode. Here is the graphical representation of growth sequence. The first, a high temperature silicon buffer layer was grown at 550 degrees centigrade, and during that this growth rate of silicon was kept 0.5 angstrom per second. And then the temperature was ramped down from a high temperature to the very low temperature value, without the growth interruption, and then we ramp down the silicon growth rate from 0.5 angstrom to nearly 0.3 angstrom per second. When this very low temperature value was achieved, then we start growing the very low temperature silicon germanium layer, and we ramp up the growth rate of germanium from 0 to nearly 0.2 angstrom per second. So we grow this very low temperature silicon germanium layer with a total growth rate of 0.5 angstrom per second. Keeping the growth rate same and without the interruption of growth, we ramped up the temperature to 550 degrees centigrade to grow the high temperature silicon germanium high temperature silicon germanium layer. Here is the detailed growth and structural parameters of clone sample are given. So in most of sample we followed the sequence which I have shown in the previous slide, except of these two samples, V41A and V45B. In these two samples, especially in V41A, we have grown this sample at a constant temperature of 550 degrees centigrade, and in V45B, we ramped down the temperature to 200 degrees centigrade, but we skipped the very low temperature growth step for the growth of silicon germanium layer. And the total thickness in all the samples was kept as 70 nanometer. In read measurements, the read pattern was recorded at the end of each growth step. Here in figure A, we can see the growth read pattern was taken after the growth of silicon buffer layer at 550 degrees centigrade, and we can see 2x1 pattern, which indicates that the surface is very smooth. In the figure B, we can see the read pattern taken from the surface of a commercial virtual substrate with the germanium concentration of 20%. And this pattern was recorded after the thermal annealing of the surface, and we can clearly see the 2x1 pattern indicates that the surface is smooth, but still we can see the streaky pattern that shows the presence of 2D roughness on the surface. When we ramp down the temperature from 550 degrees centigrade to the very low temperature value, we see that the 2x1 pattern starts to convert into streaky pattern, indicating that 2D roughness start to appear on the surface. But as we approach the very low temperature value, the streaky pattern start to be broken. So that also indicates some 3D roughness also start to appear on the surface. After the growth of very low temperature silicon germanium layer, we can see a clear bulk pattern indicating that the surface is dominated by 3D roughness. And we have also seen that in a very low temperature growth step, when we decrease the temperature from 200 degrees centigrade to 130 degrees centigrade, the intensity of these spots decreases, indicating that the periodicity of single crystal start to degrade and it tend to become polycrystalline. And in the last set of figures, we can see the pattern, the read pattern recorded after the growth of whole sample, and we can see the bright bulk patterns in the first three samples, indicating the recrystallization of the surface, and some streaky pattern can be seen for the sample which has a very low temperature growth step at 200 degrees centigrade. So it shows the re-smoothing of the surface as well. But for the sample which has a very low temperature growth step at 130 degrees centigrade, we have seen that the surface has become polycrystalline because we can see these amorphous rings. Here we can see the 113 reciprocal space maps for different samples. In asymmetric 113 reciprocal space map, if the silicon peak and the silicon germanium peak are aligned along 113 direction, the surface will be relaxed. But in figure A, which represents a reference sample which has grown without very low temperature growth step, that shows that the surface is not relaxed. It is relaxed, but it is partially relaxed. And it also shows, we can clearly see silicon and silicon germanium peak, and that indicates a good crystal quality of the structure. In figure B, which represents sample V41D, which has a very low temperature growth step at 150 degrees centigrade, shows that the surface is relaxed, but the silicon germanium layer quality is not good because the silicon germanium peak is quite broadened. In figure C, we can see the reciprocal space map from the commercial virtual substrate with 20% germanium concentration. So we can clearly see that the surface of this silicon germanium virtual substrate is fully relaxed because the silicon and silicon germanium peak are aligned along 113 direction, and we can clearly see silicon and silicon germanium peak indicating a good structural quality of the surface. In figure D, which has been grown, shows the sample V38, which has grown a very low temperature of 175 degrees centigrade with a high growth rate of 0.8 angstrom per second. We cannot see the silicon germanium peak in it. That indicates that the surface has become polycrystalline. Here we can see the AFM images from different samples. In figure A, we can see the reference sample which has a surface roughness of 2.3 nanometers, and we can see crosshatch features which are due to the dislocations in plane 110 direction. And in between these crosshatch features, we can see undulated features and some interesting features like quantum fortress, which was reported by an American group. That can also be seen in this sample. In sample B, we can see the surface of commercial virtual substrate. It also has crosshatch features, but it has very low surface roughness of 1 nanometer. We have seen that as in all samples having very low temperature growth steps, we cannot see the crosshatch features in those samples, and we can see the elongated islands and some large grains on the surface. And we have also observed that as we lower down the temperature for the very low temperature growth step from 200 degrees centigrade to 130 degrees centigrade, these elongated island starts to shrink, as we can see in the sample V45A, which has a very low temperature growth step at 130 degree centigrade. And we can see a lot of large grains on the surface. So here is the summary of AFM and XRD 2D reciprocal space map results. And we can clearly see all those samples which have very low temperature growth step, they have quite high relaxation, but they also have very high surface roughness. And the samples V41A and V41B, in which we skipped that very low temperature growth step, they have very low relaxation, but they have a low surface roughness. Here is the comparison for the relaxation and surface roughness is given with respect to the value of very low temperature for silicon germanium layer growth. And we see that if we decrease the temperature for very low temperature growth step from 200 degrees centigrade to 130 degrees centigrade, the relaxation increases and the surface roughness, it also increases. So during this work, we have found a temperature process window to achieve highly relaxed silicon germanium relaxed buffer layer in between 150 degrees centigrade and 130 degrees centigrade for the growth rate of 0.5 angstrom per second. And we have also seen this phenomena observed this phenomena that if a high growth rate can shift the temperature process window to the higher value, as we have seen in sample V38. It was grown with the total growth rate of 0.8 angstrom per second, and the surface became polycrystalline at 175 degrees centigrade. And we have also seen that the surface roughness value and the relaxation shown increasing trend with the decrease in very low temperature value for silicon germanium layer growth. But E. Casper, he reported that the relaxation increases and the surface roughness decreases with the decrease in the very low temperature value for the silicon germanium layer growth. And after comparing our grown sample with the commercial virtual substrate, we have seen that our grown virtual substrate with very low temperature growth step have quite high relaxation, more than 80%. They have very thin silicon germanium silicon germanium layer having a thickness of 70 nanometers, but the surface roughness is very high. So some suggestions for the future work. First, more work is needed to be done to find out the discrepancy we found in our results and E. Casper's results in terms of relaxation, surface roughness with respect to the change in temperature. During the present work, we study the temperature effect on the silicon germanium layers in terms of relaxation, in terms of surface roughness and high relaxation. But I suggest that we should study the thickness effect of silicon germanium layer, also study to see the variation in surface roughness and the relaxation in the surface. Thank you very much for your attention. That's all.
Thank you very much. I leave the word for the questioning.
First of all, thank you for the presentation. It's very clear and nice. And the slides are very clear. Yeah. And your thesis is citation and writing is very fluid. And here are some one comment that I think the names of samples are quite confusing for me. At least for V41, 42, it's not. I think the condition should be more clear when you write, not only the names of it. Yeah. And the questions. The first one is, please turn to slide 10. Yeah. Here you mentioned about there are two types of RSM were taken. And why you choose 004 and the 113 as a reciprocal lattice point? Why you choose this direction to calculate?
Okay. First of all, we can see the reflection from the surface in terms of structural form factor. We will see the reflection from all the surfaces which have Miller indices in case of FCC structure, which have all even Miller indices and having all odd Miller indices. So we can use those reciprocal space points. And in this case, I can draw it here. When we say symmetric, right? So symmetric reflection means it is from the reflection from the surfaces which are plane to the parallel to the surface. So those points can be 004, 008, So we have taken this 004 reciprocal lattice point, and in case of 113, this is, here we have seen the asymmetric reciprocal space map. So the asymmetric reflection should be inclined to the surface. So it would be in this direction. So it can be 1, 1, 3, 2, 2, 4. So we have taken 1, 1, 3 in this case because the incident angle is very small, and it has and it made it more surface sensitive. Yeah. So.
Okay, so you can choose 2, 2, 4 as well, but you choose 1, 1, 3.
Yeah.
This one.
Yeah.
Okay. And please turn to slide 15.
Yeah.
Yeah. And the first line of the figure, there are some lines, not
This line.
yeah. The smaller lines. What are
Or
the
these
lines?
ones.
Yes.
These are the Kikuchi lines.
Uh-huh.
Yeah.
So the reeds has Capuchin lines as well.
Yeah. Basically, we can see these Kikuchi lines, which are the spectral lines, which are seen after the diffraction of electron from any crystalline structure.
Okay.
Yeah. So
And the separation of the D, I mean the perpendicular line, the separation of D is, I think it's much larger than those three, those A, B, C. But why? Why the separation of D is larger than A, B, C?
okay. One reason can be that we used a novel digital camera to take these patterns. So we may have zoomed in more to take this pattern. So that's why there can be more difference. But there can be another difference, as you have seen in our results, that there is different germanium content in different samples. So the lattice parameter is different. So that's why you can see the spacing between the spots is different, I think.
Okay.
Yeah. But the main reason is that I think
The zoom.
yeah.
Okay. And slide 11.
Yeah.
Here you mentioned about you introducing a lot of point defect into the sample, but why do you introduce this point defect other
Sorry?
than why are you sure why do you introduce this point defect?
Sure means that we have these point defects, or
Why don't you think it's a line defect or something flame defect or else defect?
at very low temperature, I think that the atom which comes to the surface, it has very low mobility. So there must be disordered growth. So due to this disordered growth, there can be some vacancies or interstitial items like that. So these are the point defects, I think.
So you think because the low energy, so there is only can happen point defect other than line defects, or
Can be. Yeah.
so okay, I think that's all my questions.
Okay, thank you very much. Then I leave the floor to anyone who has questions.
What is the size of your virtual substrate? 2-inch substrate?
Means.
The size?
Yeah, it's a simple. It's been grown on 2-inch.
2-inch.
I forgot the sample size. But on a full
Full wafer.
Well, full wafer, yeah.
But how you can put it? How you use IFM? Because IFM, for IFM you need like small.
But after growing it, we cut it.
Oh, you cut it.
Yeah.
Oh.
After growing, we cut the sample to have different samples.
Any more questions? Since you notice this difference between your results and Casper's results, have you any suggestions on the difference? I mean, should we trust your results and not Casper's results? Or should we do the opposite?
I'm not sure, and I think we should do more work or more experiment to make it sure that we are right or they are right. Yeah.
Okay. It seems that you're ethic anyway, right? So one should, from that point of view, trust your data that it's not just a single sample, it's a number of samples.
So in that sense, yeah, it is more trustable.
Yes. Show confidence.
Yeah.
Or maybe you can, do you remember how Casper characterized his samples?
During the growth, they used that reflectivity mean to monitor the growth, and I think to measure the relaxation, something like the germanium content, they use Raman spectroscopy technique.
So in some way, I think your measurements are more easy to interpret than his measurements. Okay, are there any more questions?
In the AFM image where you were showing the causation patterns, there were basically some holes which you call fortress. I don't.
No, these are. I'm not calling these holes as a fortress.
What are these holes?
These are basically pits, but why these are can be the bunch of threading dislocations. Can be, but I didn't.
How deep they are, right?
No, we didn't. Basically, we didn't check it.
We did.
How deep they are?
About 40 to 30 nanometer.
Is that close to the layer thickness?
Now the total layer thickness is 70 nanometer.
So it's
It's
around 50%.
yeah. And they clearly show a 90 degree interwhorl angle.
How much?
It's 90 degree.
9 degrees.
It's corresponding to 105 facet. It's very well agreed with the report value for the quantum fortress. It's typical facet growth around the island surrounding the piece.
So in a way we can say other people have seen similar things, right?
Yeah.
Any more questions? Okay, if there are no more questions, then I declare the presentation as finished. Thank you very much.
Thank you.
Pass or not pass?